Today, you're not going to have any bankers on stage. Today, you're spending the day with a group of physicists who will be here to explain to us what we used to think is science fiction. There will be some technical components, but this is not a masterclass in physics. This is a group of people who are working on this full-time, coming to tell us why it matters, what we know, what we don't yet know but should be thinking about, and how this will transform our industry. Without further ado, I would like to invite our first speaker, Professor David Riley. He is a professor of physics at the University of Sydney. He also works for Microsoft, which may not be the first thing you expect to see on stage when you hear about quantum, but actually it's a reminder, if nothing else, of how close to home this will be very, very soon.
Just over 100 years ago or so, Einstein told us that, in fact, light has an alter ego, a dual personality. It behaves like a wave, oscillating at electric and magnetic fields. But light also has a different personality. It's particle-like. Light comes in chunks, in packets, in quanta, photons in our modern language. And that description of light, both wave and particle, set up a complete revolution in the way in which we think about physics. Light travels as a wave, sound travels as a wave, but the stuff we're made out of, atoms and molecules, the chairs you're sitting on, this is not wave-like objects. This stuff is tangible, touchable, real, solid particles. Or is it? How do you compute with waves? A good quantum algorithm will encode the correct answer in the constructive interference. That is to say, the right answer is going to be the wave that emerges as all of the peaks come together. The wrong answers need to cancel one another out. They need to deconstructively interfere. Quantum computing, first of all, exploits the wave-like character of nature, those orbitals, those resonant modes of electrons and other quantum objects, and then encodes information in their amplitude and phase of those wave-like objects. But one has to be very clever and very careful to set up the problem and to devise an algorithm in which the information is processed in this wave-like way. The right answer emerging from the constructive interference and all of the wrong other possible answers cancelling one another out, destructively interfering. The really challenging thing for, I think, the whole community in this area of quantum computing, whether you're looking in, wondering what it's about, how it affects your business, how it affects your ecosystem, or you're part of it, carrying out research, the real challenge is that we're still discovering the most basic fundamental aspects. We're still understanding the very laws of nature. At the same time, we're thinking about, how do I use it? How do I build a machine? How do I use that machine? How do I use it to make money? What's the business model? What are the customers? And we're still working out the basic physics. The reason this is happening in parallel, the reason we're not waiting until we understand everything perfectly well and then move on, is because history tells us that new physics rapidly, in a blink of an eye, leads to revolutions in technology. You can look at the laws of physics relating to thermodynamics and the Industrial Revolution. More to the point, the mathematical equations of light, electricity, the telegraph, the radio, television, computers, our modern economies. The physics of our modern economies is very much the physics of electromagnetism, derived from those equations. Today, we're in an amazing place in time. Around the world, various research groups, both in industry, academia, government labs, are trying to scale up this technology, trying to take it from a few working devices, a few prototypes, into a machine. That machine, even a small-scale machine, we already glimpse will have tremendous impact in a range of different technologies, spanning computing, of course, but also sensing, medical imaging, metrology, measurement science, information security, transactions, the way in which we protect our precious data, and most exciting for the scientists, fundamentally new physics that tells us about the nature of reality, tells us about our universe. It's pretty exciting to realize that not all is known. Even when it comes to basic physics, we are learning, we are peering into that dense fog and learning new things. And very quickly thinking about how we're going to exploit that physics for new technologies. Microsoft is attacking this problem at all levels. We're building out qubits, the basic building block of a quantum computer, like the transistors that encode bits, the qubits that encode quantum information. We need to not only construct large numbers of them, but our qubits need to be able to protect quantum information for long enough that it can be processed, that it's useful. Microsoft is building out classical hardware that talks to quantum computers, that talks to qubits. The truth is, if I had a quantum computer in my back pocket and gave it to you, today we don't possess the classical technology that would allow us to even control that quantum system. We need very sophisticated new devices that are going to interface with the quantum realm. A lot of fake news in quantum computing. What is a quantum computer? The way I've described it today is that it is a machine that exploits the wave-like character of nature. Is that a quantum computer? What do you mean exploit the wave-like? What's wave-like? If I do it a little bit? Is that enough? What if I do it in a way that doesn't actually connect to the problem I'm trying to solve? Is that a quantum computer? We really need to be aware in this field, and I think as I look across the finance and banking industry, the challenge is going to be recognizing when something is real. And you're going to hear a lot of noise about quantum computers and what they can do and how they're going to disrupt your industry. While I think that that's true, I think the bigger challenge in the near term is knowing when it's not true and explaining to your customers and your ecosystem how that doesn't matter right now. So there's two messages there. Get ready, but also get ready to understand enough that you can easily put it aside. Let me wrap up. Where we stand today, very similar to Edison, very similar to those other industrial revolutions. We're in possession of the basic physics. We can write down the equations of quantum mechanics. We can test those equations and build out basic devices in the laboratory. We're scaling up quantum systems into full-blown machines. If we can do that, as those machines come alive, we already know that they're going to have tremendous impact in areas related to the environment, the discovery of new material systems, and potentially even impact the way in which machine learning operates when we're dealing with quantum data. These are the applications, as impactful as they are, that we see without the hardware. As that hardware arrives, you can just bet how many more new applications are going to appear. Preparing for that day is something I think that all of us need to be cognizant of.
Talk to us about the hardware requirements and also what ownership might look like for quantum computing.
I've recognized the hardware is really complicated. Developing that hardware is going to take a completely different approach than the way in which research has happened before. I would say, if you look at a classical computer, again, the types of things you'll find in phones, what does it take to architect the processor in your phone? Those devices are an evolution over decades of many, many hundreds of thousands of people and many billions of dollars in order to produce that technology. It's based on physics that we've understood for 400 years in some ways. So quantum computing is a different beast. Seeing that technology realized is going to take the biggest industries of the world in partnership with thought leadership in academia, government labs. It's going to take financial resources, and it's going to take, I think, an ecosystem that has to come together to produce the talent, the people, the whole thing, to see it realized.
For those of us who are all now starry-eyed and actually inspired to do more, given that the journey is long, the use cases are undefined, what would your advice be on how to take this back to our organizations?
I think my message would be, I really do think it's a problem that is going to require the large tech giants of the world to make it happen. I don't think you're going to see startup company X build out hardware at a level that is going to transform things. I think it's very expensive, and it requires much more than just money. I mean, it requires ecosystems and networks. Recognizing that, though, partnering with those larger companies, partnering with academia to understand the technology and be part of the process, part of the conversation, I think is the way in.
How much of this do we need to really be able to understand to bring value to our organizations?
Having people that can understand enough to speak that language, understand enough to be able to recognize that a competitor's claim, in fact, is not really what they say it is, and to be able to put that in plain language to a customer. I have no easy answer for you there. I mean, it's computer science, it's mathematics, it's physics, it's chemistry, it's engineering. Even in academia, being a professor in physics is not enough. It's a cross-disciplinary field, let alone how to cross over into a different application and industry sector. So it's a problem we all face, and I think the way in which we have to solve it is by coming together and doing that regularly, asking that question of academics, asking the question of thought leaders in the area, putting pressure on governments to help coordinate these discussions and this work. I think is going to be critically important, but no easy answer.
For now, please put your hands together for Professor Riley.
Thanks.